Bernoulli equation is an equation of the form y prime plus some function of x times y equals some other function of x times y to the n power. In fact, we can classify this equation as a non-linear differential equation because look at the power of n unless n is 1. Well, we'll see about it. Okay, so this particular equation, if we didn't have this term y to the n, that is, if n were a 0, then the equation is actually a first order because what is that? Y prime plus p of x y equals some function q of x. But what about y to the 0? Y to the 0 is 1, isn't it? So that looks like the linear first order equation. And even better, if n equals to 1, so y prime plus p of x, y equals q of x, y to the first power, which is 1, which is y to the first, okay? Well, actually, we could do a little bit of work. Let me just quickly do y prime equals qy minus py, and that's y prime, and then this would be y times q minus p, and then we can separate the variables. Y prime over y equals q minus p. And that's actually a separated equation, right? So, all right. So how do we go about solving a Bernoulli equation? So a Bernoulli equation relies on the substitution b equals y to the 1 minus n. All right, guys. So this is really a pattern. What do we have so far? So far, we have dealt with separable equations, and then they were followed by linear first order equations. But what was the trick to solve a linear first order equation? To turn it into a separable equation and then solve it. Now, Bernoulli's equation, the magic touch of solving a Bernoulli equation is to turn a nonlinear differential equation into a linear one, which at the same time becomes really separable, right? So that's achieved by doing this substitution. V equals to y to the 1 minus n. Let's see how that works. Okay, let's have a look at one example. Well, a couple of examples. Y prime equals 4 over xy minus 6xy squared. Okay, number one, let's write the equation in the general Bernoulli's form. Actually, for this, I would need to move the 4 over x term to the left hand side. So y prime minus 4 over x y equals negative 6xy squared. All right. Now, first thing we do is identify the value of n. That is the exponent of y on the right hand side of the equation. So in this case is n equals to 2. All right. Now, what do we do next? Okay, so let's do the substitution. So y equals, oh no, v equals to y to the 1 minus n, which is v equals to y to the 1 minus 2, which is v equals to y to the negative 1. Okay, this is what we do when we do the substitution. Okay, so I'm going to solve for y. Solving for y, what would you do to solve for y? Wouldn't you raise both sides to the negative 1? Or send the y to the negative 1 to the denominator and do some cross multiplication. That's not going to work for every single one anyway. So this would be y equals v to the negative 1. All right. That's because I would need to write down the derivative in terms of v. Notice in this case, it's important to clarify that these are two functions of x. All right. So let's take the derivative. dy dx equals, okay, the derivative of v to the negative 1, that's negative 1, v to the negative 2. But because this is an implicit function of x, we would need some sort of chain rule here. That is, we need to multiply by the derivative of v with respect x. All right? So what do we do? So now let's do the substitution. So for the substitutions, we're going to replace dy dx equals what we just got over here. That's the y prime, isn't it? Well, actually, technically here. Okay. And I'm going to replace y equals to v to the negative 1 over here into the y. All right. Let's do the substitution. Let's see what happens here. Okay, so number one, y prime, which is really negative 1, that's just negative v to the negative 2 dv dx minus 4 over x y. Well, actually, what's y? Wasn't v to the negative 1? So we're substituting everything in terms of y. Oh, I forgot to also highlight it here, okay? And that equals negative 6x quantity squared. What's the quantity squared? Another v to the negative 1. All right? Well, let's simplify this. And guys, well, it seems like we're getting an equation that looks more complicated than the one we started with. You'll see the magic in a second. So, okay, negative v, negative v, negative v, negative 2 dv dx minus 4 over x v to the negative 1 equals negative 6x v to the negative 2. All right? So the purpose of the substitution here that we just did is to kill that nonlinear term to turn the differential equation into a linear one. Okay, so the general form of the linear equation is to have the dvdx with a coefficient of 1, isn't it? So this is what I'm going to do. How do we cancel this negative v to the negative 2? There's a couple of ways. So I'm going to multiply both sides by negative v to the second power. Do you guys agree with this? Negative because to cancel the negative, and v squared times v to the negative 2, boom, they cancel out, right? And then we're going to do some algebra afterwards. Don't worry, okay? So now, negative v squared distribute and distribute, okay? All right, so negative is positive, this v is canceled, we get dv dx. Okay, what about negative v squared times v to the negative 1? That's essentially a 2 minus 1 in the exponents. Okay, so, okay, negative times a negative is positive, 4 over x. And well, let me write this down. V to the 2 minus 1 equals to negative 6x. Okay, what about this v to the negative 2 times v to the positive 2? The v's cancel out, and also negative times a negative, actually, this is positive. So 6xv or vx. No, 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 just x, 6x, right? All right, 2 minus 1, so that is dv dx plus 4 over x v equals to 6x. Did you see the magic of the substitution? Isn't that a linear first order equation? We got rid of the nonlinear term again, which at the same time this equation will become separable, but actually I showed you a formula rather than the long process to solve a linear first order equation. Okay, so let's identify our, remember the p of x and everything else? Okay, the p of x, which is whatever multiplies the v, in this case would have been y, right? But in this case we're in the world of v. That's 4 over x, and f of x equals c of 6x, right? Okay. Now let's find the integrating factor, mu of x, by evaluating e to the integral of 4 over x dx, which is e to the 4 ln of x. But just like last time, we cannot cancel the ln's. Let's basketball the coefficient, remember? And then we would be able to cancel e with ln, x to the 4th power. Cancel, cancel. The integrating factor mu of x equals x to the 4th. All right? Okay. So, guys, so let me continue on this side right here. So the formula I gave you to solve a linear first order differential equation, that was y mu equals to the integral of mu f dx. However, we are not in the world of y at the moment. Remember, we are in the world of v, really. Okay, so this becomes really v mu equals to the integral, okay, still mu f dx. Okay, so now let's substitute what we have. That is v mu, which is x to the fourth, equals the integral of mu, which is also x to the fourth, times f, which is 6x dx. And then v, x to the fourth, equals to 6 times the integral of x to the fifth dx. And while the integral of x to the fifth with respect x, isn't that 6x to the 6 over 6 plus c, x to the fourth, v, and vx to the fourth equals to x to the 6 plus c. We're essentially done. We're almost done. Let's solve for v. Let's solve for v by dividing both sides by x to the fourth. So v equals to x to the 6 divided by x to the 4. Is that x squared plus c over x to the fourth? Okay. And guys, that's essentially the solution. Well, actually, you know what? I'm going to write the solution in a slightly different way. X to the 6 plus c over x to the 4. You will see why I'm leaving it in these terms instead. So we're done with solving the differential equation. However, we need to back substitute for our variable v. What did we say about v at the beginning of the problem? Remember? So v, wasn't that y to the negative 1? Okay? So v equals y to the negative 1. Okay? So back sub y to the negative 1, x to the 6 plus c over x to the 4th. Okay, so that's essentially y, 1 over y, isn't it? So 1 over y equals to x to the 6 plus c over 4. And we can easily solve for y by flipping both sides of the equation or doing a cross multiplication. I think the flipping both sides just works better. So that was x to the 4th, not 4. Thank you, thank you. Hmm? So really the solution would be y equals to x to the 4th over x to the 6th plus c. And that is our first Bernoulli's equation example. All right. Let's have a look at the next one. Let's have a look at the next example. Okay, we have one more, and I think that's about it, right? Okay. So we have the equation dy dx plus 1/3 y equals to e to the x y to the fourth power. All right, so this is a Bernoulli's equation because we have the derivative term plus some function of x. I know there's no x, but that 1/3 is technically a function of x times y to the first power equals some function of x times a non-linear term of the, or factor rather, of the dependent variable. Okay, so let's identify the value of n. Isn't that 4 in this case? So n equals to 4. All right, let's perform the substitution. So for the substitution, we so that is v equals to y to the 1 minus n, which is v equals to y to the 1 minus, what is that? 4, which is v equals to y to the negative 3. Again, I would like to get the y by itself. What would we do to get the y by itself in this case? Help me out here. Hmm? This could be a weird one, right? Okay, let me. Uh, one way is to raise both sides to the negative 1/3. Are you guys okay with this? Or if you prefer, if working with negative fractions like this kind of bothers, okay, that's v equals to 1 over y cubed. All right, cross multiply y cubed equals to v. 1 over v, rather. Wait a minute. Yeah, 1 over v. No, you know what? Never mind. Let me do the negative exponent. Let me do raised to the negative 1/3 and raised to the negative 1/3. Okay, much better. I feel safer this way. Okay, so because negative 1/3 on the outside multiplying with the negative 3 in the inside, that outputs a 1 as a power overall, right? So that'll be a y equals to v to the negative 1/3. Okay, so now we need to take the derivative of this dy dx. Okay, the derivative of v to the negative 1/3, that is negative 1/3 v to the negative 1/3 minus 1. Isn't that negative 4/3? Okay, but in this case, we are multiplying by dv dx. So it seems like we have everything we need to substitute into the differential equation. So I'm going to substitute the derivative, okay, into this term right here, okay, and y equals v to the negative 1/3 right here and right here, only for the y, not take into account the fourth power. All right. Okay. Yes. So the next couple of steps may look ugly. I mean, there is no way around it. It's what it is, you know. But we're gonna get to a nice equation. I promise you. All right. So negative negative 1/3 v to the negative 4/3 dv dx plus 1/3 y, which is v to the negative 1/3, equals e to the x v to the negative 1/3. But notice this is supposed to be raised to the fourth power. I know that doesn't look any easier, but we just need to handle these ugly exponents for a couple of steps only. All right. Okay. So number one, let me clean. Let me do some cleaning. Okay. I'm gonna move. Okay, I'm going to raise the powers here. So that is negative 1/3 v to the negative 4/3 dv dx plus 1/3. I'm not doing that much right here. Just the powers equals e to the x v to the negative 4/3. Okay. So what's the goal here? Our goal is to make sure the dvdx term has a coefficient of 1. So we have that negative 1/3. V looks like a y, but it should be a v. Okay. V to the negative 4/3. So we need to divide by that quantity, but that's going to look like a weird division. Let me do one step at a time instead. First, I'm going to multiply both sides by negative 3. That actually helps with the sign. And to cancel the 3 in the denominator, that'll be positive v to the negative 4/3 dv dx plus, oh, actually minus, right? 3 times 1/3, that's another minus v to the negative 1/2. No, not 1/2. That's actually 1/3, right? Thank you, right? And equals e to the x v, well, actually, negative 3 of them, right? Negative 4/3, right? Okay, so at this point, you have two options. You might want to divide by v to the negative 4/3, or alternatively, multiply both sides by v to the positive 4/3. Do you agree with this? Because when distributing and multiplying the bases, the exponents right here are going to add up to 0. All right. And then the v to the 0, that's the one we're looking for. Okay. So that is v to the 4/3 multiplied by v to the 4/3. Okay. So when distributing, v to the 4/3 times v to the negative 4/3, they add up to v to the 0, which is 1. That leaves us with dv dx minus, oh, check the magic here. 4 thirds minus 1 third, how many thirds? 1 3 thirds, which is 1. Wasn't that the magic? Equals to negative 3 e to the x. Negative 4 thirds plus 4 thirds, that's simply, they go away. Did you see the linear first order equation? This substitution was useful to kill that nonlinear term, to turn the equation into a linear one, which at the same time is essentially a separable one. But again, I gave you a formula. All right. Okay. Well, let's evaluate. Or let's solve this differential equation, this linear first order. So p of x. What's p of x? Negative one, and f of x, negative 3 e to the x. All right. So integrating factor. Okay. Let me do the integrating. How much space? Okay. Let me do the integrating factor. Did I use a different color for that? What did I? No, I think I used. Yeah. Okay. Getting the integrating factor mu of x equals to e to the integral of p dx, which is e to the integral of negative 1 dx, which is mu of x. That's simply e to the negative x, right? That's the integrating factor. Again, uh, y mu equals to the integral of mu f dx. Well, in this case, we're not using y. We're using v. We're still in the world of v, not in the world of y. Integral of mu f dx. And the rest of the problem, substitute, evaluate the integral, and you got it. So that's v mu e to the negative x equals the integral of mu, which is also e to the negative x, times our f of x, which is negative 3 e to the x dx. Well, let's do a little bit of algebra in the integrands. Number one, I would like to take the negative outside of the integral, negative 3 e to the negative. Oh, wait a minute. Wow, this is nice, isn't it? Because e to the x cancels with e to the negative x, and that's simply negative 3 times the integral of the x equals e to the negative x v, okay? So that is v e to the negative x equals to negative 3x plus c. So we should be good. Divide both sides by by e to the negative x. Okay, let me do that. And v, okay, let me continue here. And v equals to negative 3x. Can we move this e to the negative x to the numerator with positive exponent? How about that? E to the x and plus c e to the x. And well, we're essentially done, except what did we say about v in this case? What was v? Let's go back to the top. The substitution, the magical substitution. V, wasn't that y to the negative 3? Yes, y to the negative 3. But v equals y to the negative 3. So y to the negative 3 equals to negative 3x e to the x plus c e to the x. Okay, I don't like this negative exponent. Let me write it as a y over y cubed equals to the same, negative 3x e to the x plus c e to the x. Well, how about we flip both sides of the equation? So that is y cubed equals to 1 over negative 3x e to the x plus c e to the x. And to get the y by itself, what do we do? Cube root negative 3x e to the x plus c e to the x in the denominator of 1. We're not done yet. We need to box our final answer. And that's the end, right? That's the end of the topic.